Deep within the Taurus constellation, about 6,500 light-years from Earth, lies the breathtaking Crab Nebula, one of the most significant celestial objects cataloged by astronomers. First observed in the mid-18th century, it was soon connected to a massive supernova explosion that had illuminated the sky in the same location roughly 700 years earlier. Since then, the Crab Nebula has remained a focal point of scientific curiosity, becoming one of the most thoroughly studied objects in the universe. As technology has advanced, so has our understanding of this enigmatic nebula, continuously revealing new surprises. By the late 1960s, the rise of radio astronomy uncovered a hidden remnant of the supernova, an extremely dense and rapidly rotating neutron star. These stellar remnants, the last form of matter before collapsing into black holes, play a crucial role in enriching the galaxy with the building blocks of life. Today we delve into the astonishing power of pulsars, one of the most extreme manifestations of neutron stars. Unlike stars like our Sun, which expand into red giants and shed their outer layers to reveal a white dwarf core, much larger and unstable stars, at least 10 times the Sun's mass, end their lives differently. When such a star exhausts its nuclear fuel, it collapses under its immense gravity. Its outer layers crash into the iron core before rebounding in a spectacular supernova explosion. The fate of the remaining core depends on its mass. If it exceeds 3 solar masses, it will continue collapsing until it forms a black hole. However, if it remains below this critical threshold, it stabilizes as a neutron star, an unimaginably dense sphere of neutrons packed together under immense pressure. Neutron stars, despite their small size, around 25 kilometers in diameter, contain up to twice the Sun's mass, compressed into an area no larger than a city like Boston, Frankfurt, or Cincinnati. This extreme density drives some of the most powerful physical phenomena in the cosmos. Their outer shell consists of superheated iron trapping the violent forces within. The gravity is so intense that escape velocity exceeds half the speed of light, even affecting time itself, stretching and slowing it much like a black hole does. These stars radiate heat for hundreds of millions of years, with the closest known neutron star glowing at nearly 500,000 Kelvin. Beneath the crust lies a bizarre mantle composed of nuclear pasta, elongated structures of neutron-degenerate material, leading to a superfluid core of dense neutronium. The combination of rapid rotation and extreme compression amplifies the star's magnetic field to hundreds of billions of times Earth's strength, making neutron stars the strongest magnets in the universe. Unlike most stars, they are rarely visible in the optical spectrum. Instead, they shine primarily in radio, X-ray, and gamma-ray frequencies. As a neutron star rotates, charged particles within its magnetosphere are accelerated along magnetic field lines, emitting powerful synchrotron radiation, especially in radio wavelengths. Because the star's magnetic axis is not aligned with its rotation, these beams sweep through space like a cosmic lighthouse. If one of these beams crosses Earth, it appears as a periodic pulse of radio waves, hence the name pulsar. The first pulsar was discovered in 1967 by graduate student Jocelyn Bell Burnell, who detected precisely spaced radio pulses occurring every 1.3 seconds. Initially, some scientists speculated they might be signals from extraterrestrial civilizations, but as more such sources were found, they were attributed to rapidly spinning neutron stars. Since then, astronomers have cataloged over 3,200 pulsars across the Milky Way, with potentially billions more lurking unseen due to age and slowing rotation. Young pulsars spin rapidly, emitting high-energy radiation, but over time, they lose momentum in a process called spin-down. In some cases, however, if a pulsar exists within a binary system alongside a companion star, it can gain energy from its partner. Material from the companion forms an accretion disk around the neutron star, feeding it mass and increasing its spin rate. This process, called spin-up, can transform the star into an X-ray pulsar. If its rotation period falls below 10 milliseconds, it becomes a millisecond pulsar, one of the fastest spinning objects in the universe. Millisecond pulsars, which can rotate hundreds of times per second, provide an incredibly precise cosmic clock, sensitive enough to detect the gravitational influence of nearby objects. In fact, the first exoplanets ever discovered in 1992 were found orbiting a millisecond pulsar. The fastest known pulsar, PSRJ 1748-2446 AD, spins at an astonishing 716 times per second, with its equator moving at a quarter of the speed of light. However, some neutron stars are even more extreme, magnetars. First identified in 1979 through bursts of gamma radiation, magnetars possess magnetic fields a quadrillion times stronger than Earth's. This immense magnetism fuels violent eruptions and starquakes, which produce powerful X-ray and gamma-ray flares. With only about 25 known in our galaxy, magnetars are rare, and likely represent a brief phase in the evolution of highly magnetized neutron stars. Their intense activity, including magnetic reconnections and megaflares, makes them some of the most energetic and unpredictable objects in the universe. As these deceased stars spin, their metallic crusts endure immense stress from both directions. Internally, from intense electrical currents swirling within the superfluid neutronium, and externally from the relentless twisting of magnetic field lines on their surface. Eventually, this crystalline shell reaches a breaking point, cracking under the strain. Even a minuscule shift toward a more spherical form, on the scale of mere micrometers, is enough to unleash torrents of electromagnetic energy, including high-energy X-rays and soft gamma rays. The most powerful starquake ever detected occurred on December 27, 2004, when the magnetar SGR 1806-20 released an amount of gamma radiation surpassing 150,000 years worth of the sun's energy within a single second. Despite being more than 40,000 light years from our solar system, the residual shockwaves were powerful enough to cause a measurable increase in ionization levels within Earth's upper atmosphere. If such an event were to occur within just 10 light years of our planet, the consequences would be catastrophic. The extreme gamma radiation would obliterate Earth's magnetic shield, allowing solar radiation to strip away the atmosphere, evaporate the oceans, and render the surface an airless, irradiated wasteland. Gamma rays aren't the only radiation linked to starquakes. These violent events have also been proposed as a potential source of fast radio bursts, brief, unexplained radio signals, detected hundreds of times with no widely accepted explanation. Intriguingly, about 30 of these bursts are repeaters, not consistent emissions, but recurring nonetheless. This suggests a possible connection to soft gamma ray repeater emissions, hinting at magnetars as a shared origin. Alternatively, they might emerge from neutron star collisions, where two of these incredibly dense objects merge, setting off another series of colossal explosions. As mentioned earlier, rapidly spinning pulsars serve as precise cosmic beacons, allowing scientists to study their environments with remarkable accuracy. Using this method, physicists Joseph Taylor and Russell Holtz won the Nobel Prize in 1993 for their discovery of the first binary pulsar. Their Doppler shift measurements revealed a rapidly rotating pulsar, 1913 plus 16, gradually spiraling inward toward its neutron star companion. The shrinking orbit, caused by energy loss in the form of gravitational waves, ripples in space-time predicted by Einstein decades earlier, was the first observational evidence of general relativity at work. However, it would take another 30 years before humanity would directly detect gravitational waves, which finally happened in 2015, with the Laser Interferometer Gravitational Wave Observatory, LIGO. When two massive compact objects, such as neutron stars or black holes, spiral toward each other, they accelerate to incredible speeds, reaching up to 2/3 the speed of light. This extreme movement warps space-time, generating gravitational waves that travel across the universe for billions of light years before being detected by instruments like LIGO. These signals often serve as a precursor to pinpointing the exact location of a cosmic catastrophe. Once two neutron stars come close enough, they reach speeds beyond their own escape velocity, causing their iron crusts to rupture and exposing their super-dense interiors to the vacuum of space. Some of this material escapes, decompressing rapidly and igniting in a spectacular kilonova, an explosion as powerful as the most intense supernovae. Similar to supernova, the debris from these collisions is rich in heavy elements, fused by the rapid neutron capture process R process to create everything from iron and gold to uranium and platinum. In fact, scientists now believe kilonovae, rather than supernovae, are the primary source of the universe's heavy elements, including those essential for life. Much like exploding stars, merging neutron stars also produce their own category of gamma ray bursts, GRBS. Longer duration GRBs, lasting seconds to minutes, are linked to supernovae. In contrast, the brief exposure of neutron star interiors to space during a kilonova results in a short gamma ray burst, lasting under 2 seconds, sometimes accompanied by a fast radio burst. Soon after, the remnants of both neutron stars coalesce into a single entity, which either collapses into a black hole or forms a heavier neutron star, possibly a magnetar, continuing its evolutionary cycle. A fascinating question arises. What happens if the merged object reaches a mass that sits between these two outcomes, too massive for neutron pressure to sustain, yet not quite dense enough to form a black hole? This scenario may give rise to an exotic and highly speculative state of matter. Neutrons and protons, the building blocks of atomic nuclei, belong to a class of particles called hadrons, which are themselves composed of even smaller fundamental particles known as quarks. Quarks are the most basic components of matter, existing freely only in the extreme conditions of the early universe, when temperatures and densities were incomprehensibly high. If a neutron star accumulates enough mass to exceed the Tolman-Oppenheimer-Volkoff limit, the threshold beyond which neutrons can no longer resist gravitational collapse, its internal pressure may become so extreme that it breaks down neutron structure entirely, liberating quarks in a process called quark deconfinement. This transition would create a quark star, where matter is compressed to a state even denser than neutronium, forming a quark-gluon superfluid. Such a star would have properties akin to a giant hadron, a subatomic particle writ large. A quark star could exist in different forms. A two-flavor quark star, composed mostly of up and down quarks, would closely resemble a neutron star, featuring a quark-gluon core encased in nuclear material. However, a three-flavor quark star, containing an additional type of quark called the strange quark, would be much more stable at lower energy levels. This so-called strange star could have an inherently self-bound structure, potentially lacking a solid surface entirely. Over time, electrical currents from its core might eject residual nuclear matter outward, forming a temporary crust. However, this unstable layer would eventually collapse back into the quark core, triggering gamma-ray bursts, possibly explaining certain unusual soft gamma-ray repeaters that deviate from typical magnetar behavior. During this process, small fragments of quark matter, known as strangelets, could be ejected into space. If a strangelet were to collide with ordinary matter, it could theoretically trigger a chain reaction, transforming entire planets or stars into quark matter, though this idea remains highly speculative. Despite extensive theoretical modeling, quark stars remain purely hypothetical, as no direct observational evidence has been found to confirm their existence. Another exotic type of hybrid neutron star may have already emerged in our cosmic neighborhood. The system GROJ 1655-40, located 10,000 light-years away, consists of an evolved F-type star transferring material onto an unseen compact companion, presumably a black hole. However, the origins of the system may trace back to an even more fascinating event, the creation of a Thorne-Jit-Cobb object, TZO. First proposed in 1977, a TZO forms when a neutron star is captured by a much larger red giant, eventually spiraling inward and settling inside its gaseous envelope. The neutron star's extreme gravity disturbs the red giant's core, setting off complex internal dynamics while remaining largely indistinguishable from an ordinary red giant. Over time, the core collapses, forming a black hole, while much of the red giant's outer layers remain intact. Some scientists speculate that the unusual characteristics of GROJ 1655-40 may be the remnants of such an event. From gamma-ray bursts to the origins of heavy elements, neutron stars play a crucial role in shaping the universe. Their extreme physics not only influence cosmic evolution, but also provide essential clues about the nature of matter itself. Whether through their violent collisions, mysterious emissions, or hypothetical quark transformations, these stellar remnants continue to challenge our understanding of astrophysics. And with that, I bid you good night.